If there's no objections, I'm going to record these lectures. So not any visual recording. I got a little microphone here, and I'm recording the slides, and I'll put up recordings of my voice over the slides, if everybody's comfortable with that. If you say something, your voice will be like sort of recorded. You come across as a mild murmur. It's very directional to my voice. So if I repeat your question, it's probably to get it on the recording. If anybody's worried about that, let me know. I can like edit out your... If you say something unconscionably silly, then I can maybe edit it out of the video or something like that. It's never happened before, but yeah, okay. So I'll be putting these on Blackboard. Links to the recordings will be up on Blackboard. Okay. A bit of good news. So if you were here last time, I was slightly discombobulated because the readings that I expected to be online, I could not find online. I'm happy to say that they are online, actually. With some help from the wonderful people at the library, I found that it was, they did a switch of the search engine, and the new search engine just wasn't finding this book. So they helped me find it, and now there's a link on Blackboard. My whole first month of this class was designed around you reading the first 3 chapters of this book. So I'm very glad that it's back, and now I guess I am once again combobulated, I think is the term. So yeah, so this will be our reading. So there's nothing for this week, but starting next week, read the first chapter of this, and then each next subsequent weeks, second and third chapters. It's a really nice book. I think it's a particularly nice book for this class because Grinnell is not a professional philosopher. He's trained as a molecular biologist. And he's offering you a view from within the sciences, an insider's view of how science works, in a way that's both sophisticated and sympathetic. And he develops a whole bunch of issues that we're going to be interested in. Particularly, he develops the relationship between, so this is the everyday practice of science, subtitle, where intuition and passion meet objectivity and logic. So he's going to develop this idea that the kind of interests and values of scientists play an important role in how science works, but not that it plays a destructive role. So that values have a job to play in scientific practice, but not the kind of like, it's not a bias exactly. It's a motivating role and a structuring role. And he explains in quite a bit of depth how he thinks that works. So I think this is a really nice text. It's my favorite sort of intro philosophy science text. I'm really glad we get to work with it. I don't know what we would have done without it. So yeah, so I'm much more confident about what we're going to be doing for the next month now that we've got this up. So, okay, so last time we didn't really do all that much. I really just made the argument that philosophy of science should exist as a discipline. Because you can't get everything that you want out of just things like the history of science or the sociology of science. This central question, how does science work, of course, you can't answer that without doing some history of science, sociology of science, that kind of thing. That's a purely descriptive question. It's a question about the facts of the matter. But there's this normative question, a question about how it should work, that really can't be accessed through those disciplines. You need philosophy, you need a normative discipline like philosophy to do that. I realized I said I was making the case that I should have a job. I realized I was actually just making the case that my job should exist, not necessarily that I personally should have it, but hopefully I made something of the case that philosophy of science as a thing is required in order to answer these 2 questions meaningfully. Today, we really didn't talk about much about what we're going to do in this course. So today, really all we're going to do is just sort of talk about the contents of this course. So here's 2 enormous, broad questions. Now I propose to look at 10 more specific questions that are more or less the order in which we're going to deal with. These are in the order that we're more or less going to deal with in this course. These are kind of the major topics that we'll go through. I'll just go through for the rest of the class. I'm really just going to go through these one by one and kind of give you a broad overview of the sort of issues that we're going to be dealing with. All right? Okay, and if you missed last time, read the syllabus. Read it carefully and ask me if you've got any questions. Yeah? Okay. Okay. So we're going to start off with this question. Is science objective? And I would love it if somebody could tell me what objectivity is in the first place. Any thoughts? Yeah.
Objectivity is the belief that the universe is knowable or measurable.
So, okay. Does everybody have to come up with the same measurements for it to be objective?
Well, if people are coming up with different measurements, it implies that somebody's wrong.
Does it?
I think so.
Okay. If it's objective, maybe. There's other thoughts, yeah?
I would say that objectivity would be something in that it's you're not putting your own beliefs and biases into what you're measuring. Your own point of view is just what it is.
Okay, okay. So that makes it sound like nothing that we can ever know could be objective, because there's no seeing except seeing from a point of view, right? Everything that you ever experience comes from a point of view, right? It's in some sense selective. So if that's what objectivity means, then objectivity is permanently beyond any possibility of our reach. That seems bad. Objectivity is supposed to be a good thing, right? You want to be everybody wants to be objective, right? Yeah?
I think objectivity is like a true fact that everyone
A true fact that everybody can agree with. So something about agreement here. Something about, it's true, there's a relationship to the world, and it's something that we can all sort of get on board with, or something like that. So that sounds about right. That sounds about right. Can everybody agree on something and still be wrong?
Yes.
Yeah, probably. Yeah?
Is all of science an ad pop even?
We'll come back to that, actually. So ad populum is just sort of like the fallacy of saying everybody thinks it, therefore it's true. And of course, everybody can be wrong. I personally don't think that it is. I think there's much more to it than that. But we'll come back to that. Yeah. Okay, so I really wish, I see the words objective and subjective in undergraduate assignments all the time, and it always makes me nervous when I see them, because I don't know what you mean. I don't know what an individual means by those words when they just use them without further clarification. One thing that you might mean is everybody agrees. You might mean that it's true. You might mean that it doesn't come through a particular point of view. You might also mean that it's value neutral. Yeah? You might mean that it's something that doesn't depend on what you care about, or something like that. All of these are potential meanings of the word objective, and you really got to clarify what you mean. Before you can make any meaningful claims about whether science is or isn't objective, you really got to clarify what you mean by that. So we'll spend some time. Frederick Grinnell, the guy who wrote the readings for this first bit of the course, is going to spend some time digging into what you might mean by this. And you'd better hope that it's not the version where it's not having a specific perspective, because that means that nothing that we've ever seen or could ever possibly see could be objective. If that's what you mean by it, it's kind of a useless term, right? Because there's no God's eye view. There's no view from nowhere. Everything that you could possibly know about is known through some point of view or other. Right? I don't know how you know it if it's not through a point of view. So we'll spend some time wrestling with this. We'll try to clarify what it might mean to be objective. It sounds like something you want. It sounds desirable. It sounds like, yeah, I like being objective. That sounds good. And people use subjectives in a kind of dismissive way. It's like, that's merely subjective. So something desirable, but people aren't really all that clear about what it is or why they might want it. So we'll dig into that. That's one of the first topics that we'll kind of start digging into. So one of the things that comes along with the idea, the sort of unpolished idea that science is objective, is this model of science Grinnell's going to identify and critique. the linear model of science. I talked about this last time as a kind of just a pile of facts. So here's a pretty naive view of science that most people who think hard about this stuff haven't believed for a long time, but that is nonetheless sort of still got its hooks in the popular imagination, which is that science is a linear process. Every single experiment we do just adds to a pile of facts, and those facts always accumulate. Once in a while, you know, somebody retracts a paper and you got to pull a fact out of the pile, but almost always there's this sort of steady accumulation of knowledge. And this was pretty plausible in, say, the era when Newtonian mechanics was the paradigm of scientific research, right? For people living before Einstein, after Newton, but before Einstein, it really looked like science was just making steady progress, right? It was just adding new facts. And in fact, that it started to look like, especially for fields like physics, that it was almost done. That really it was just a matter of working out a few of the little details and then a whole bunch of sort of practical applications, of course. You want to work at the technological implications of your scientific knowledge. But between Newton and Einstein, it really looked like science was pretty much worked out. The basics of it was pretty much solidly figured out. And that there would never be a kind of radical transformation of the basis of our knowledge. Newton had figured it out. And that everything else was just going to be working out the details and the footnotes to Newton. And I don't know if you've been following along with what's been going in physics for the last couple hundred years, but that turns out not to be true. That turns out to be actually quite wrong in terms of how scientific knowledge progresses. Newton turned out not to be just wrong in detail, but in the fundamental presuppositions of his model. Newton thought that space was absolute. Turns out space is relative. Newton thought that you could always say there was an objective fact of the matter about whether two events happen at the same time. Nope. Turns out not to be. The basic outline of his theory turned out to be, in a deep way, wrong. It's still super useful, but it's not true. So this linear model of science turns out to be really not adequate for describing the history of science. If you actually look at how science has progressed over the centuries, this is not it. This is not how it happens. And it continues to not be how it happens. So the linear model of science is something that Grinnell is going to critique pretty deeply. It's simply not the case that we just add facts and facts and facts and facts, and that's what science is just a big heap of facts. It seems to be that big parts of scientific knowledge get either turned over or transformed in pretty deep and radical ways. So if what you mean by objective is can't be wrong, science is not objective in that sense. And not just wrong in the details, but wrong in its basic outlines. Yeah? It's not to say that there is some better way of coming up with good descriptions of the universe. I think science is a really good one and the best we've got, frankly. But it doesn't mean that what you get are just a steadily accumulating collection of facts that you can sort of bet your life on. Okay? So, the way in which Grinnell is going to sort of critique the linear model is by thinking about this relationship between what we might call facts and interpretations. So think, for example, about the shift from Ptolemy to Copernicus. So Ptolemy was the best model of the solar system going back when people mostly thought that the Earth was in the center and the sun goes around it and all the planets go around the Earth, right? So the heliocentric, or the geocentric model of the solar system, that was Ptolemy. And when Ptolemy stood outside at night and looked up at the stars, Ptolemy saw was the stars going around the Earth. And that's something that you can see, right? It's an observable fact. So the basis of scientific knowledge, of course, is observation. Observation is where it all gets grounded in terms of science. But what is it that you're observing? Ptolemy would have told you that he can see the planets going around the Earth. He can see the sun going around the Earth. And if you look at it through that lens, you can see that too. When Copernicus came along and developed the heliocentric model of the solar system, he saw something different. What we actually see seems to change over time. Yeah? So it's not just that you passively receive data from the universe unfiltered by your ideas or your interpretations. Right? Even at this most basic level of what do I see when I go and look up at the night sky? That's not something that's just out there for you to grab onto. It's something that you both, I mean, it's not the case that you just sort of intuit whether the Earth goes around the sun or the sun goes around the Earth, right? This is not something that you sit indoors in your armchair and work out, right? You need to make these observations. Of course, Copernicus was working intensely with careful observational data. But just having the data doesn't give you the theory. You interpret the data. So you are bringing some active interpretive process to the data, making sense of it, making it into a coherent, meaningful whole. Yeah? So we're participating in, maybe you might even say, the constitution of the data. Right? Because a bunch of numbers on a page aren't data. Having an interpretation of those numbers is what makes it into data. So our theories, Grinnell's going to argue, and I think this is right, play a role in making our observations into observations. Like just photons hitting your eyeballs is not enough to say you've made a scientific observation. You have to fit it into some meaningful framework in order to make inferences from it, in order to make conclusions from what you're looking at. And Grinnell's going to make that case. His examples are mostly drawn from 20th, 21st century biochemistry. So it's not just like this happened once in the 1500s and then we were done. We continue to make observations within theoretical frameworks, and the theoretical frameworks kind of come together with the data to make them meaningful observations. Yeah? So, the point is just that it's not just like that there's facts lying around. So here's the linear model. There's just sort of facts strewn around on the ground, and what scientists do is go pick them up, put them in a pile. And that just really doesn't seem to be adequate. If you know anything about how the history of science has gone, that really doesn't seem to be an adequate picture of how things work. Now, is what I'm saying that science is in some sense unreliable? No, I don't think that's right. That's not the case that Grinnell's going to make. It's not the case that I'm going to make. It's not that we should be skeptics. It is, however, the case that we can't be naive about this process. We can't sort of be like, well, those are just the facts, right? Because we help to constitute the facts. We and the world come together to constitute facts, rather than the facts just being objective in some sense. So another big issue that we're going to talk about and that Grinnell's going to deal with is the relationship between science and values. Values being the things that you care about. And this is at the very beginning, I mentioned this is a potential way in which something might be, the objectivity of some research program might be compromised. Yeah? So, does what we care about influence science? And the case that Grinnell's going to make is that yes, it does, always, but sometimes in a good way and sometimes in a bad way. So if you find out, for example, that the pharmaceutical company that's selling the drug ran the trial that approved the drug, you might worry about that. You might legitimately wonder how careful they were in their analysis, how did they treat their data, were they looking for a result, or were they open to the possibility that this thing that they spent $10 million on might fail? And in that case, their values might actually compromise the scientific process. But we don't want to always say that having values compromises the scientific process, because all scientists care about the outcomes of their results, or their outcomes of their experiments, their outcomes of their studies. I mean, all scientists are engaged in a competition for grant money. So I don't know if they've explained this to you budding scientists, but they don't just sort of set you up in a lab for life and say, go to it. You have to constantly convince grant boards that what you're doing is worthwhile and interesting. So that's a built-in motivation to think that what you're doing is on to something. It's not like you just have a rich, full, you don't get to have a rich, full scientific career just coming up with null results. If you just keep coming up with null results, you don't get to be a scientist anymore. So your whole professional livelihood is on the line for coming up with something novel and interesting and sort of like compelling to grant boards, basically. Yeah? So every scientist has built-in motivation to come up with some result or other. Does that mean that all science is compromised in the same way that when the pharmaceutical company is testing its own drug? You better hope not. Yeah? You better hope that there are ways in which our values can influence science that are okay, and ways in which it's not okay. Yeah? So Grinnell's going to make the case that it's not just scientists. All of our observing is value-laden in some sense. What you care about is going to help pick out things for you. What you care about makes some things jump out at you and some things not jump out at you. Yeah? This is just a fact about human psychology. So somebody who is deeply interested in fashion will see very different things when they walk down the street than somebody who's very interested in, I don't know, how people walk, right? So if somebody's a physiologist, they're looking at people's gait, they're looking at how people hold themselves. That's going to be a whole different set of things are salient to them, that jump out at them, that seem relevant to them, than somebody who is profoundly interested in how people dress. Yeah? So all of our observation is actually structured by what we care about. There's just way, way too much information available to us all the time to pay attention to all of it. So paying attention to something is in some sense valuing it, in some broad sense. Yeah? So this is just a fact about all human perception, that it's structured by our values. And the same thing is going to happen in science. We'll talk about paradigms. And in sort of a paradigm is in some sense a set of things that a particular science at a particular moment thinks is important, thinks is worth studying, thinks is worth doing experiments on, making observations about, and reporting on. So a paradigm it's like a framework. In some sense, it's like a value system. Now, that's not the same as saying that it's a value system like I'm a right-wing guy or a left-wing guy. It's not the same as a value system in like I love mashed potatoes or something like that. So there's a whole range of different kinds of values, some of which might be genuinely destructive or corrosive to the integrity of the scientific project. Like if you just love getting grant money so much you're willing to falsify your data, that's obviously corrosive to science, right? Like if you care more about your personal success than scientific integrity, nobody would argue that that's okay. And I think that there's a profound difference between that and the kind of things jumping out at you because you think they're interesting or important, or because you care about them. Yeah? So we should be careful about this. We should be sophisticated about, Grinnell's going to argue, the different ways in which values can potentially play a role in science, and not be kind of blunt about it. So the blunt way of talking about this is just to say, facts are facts. This is the facts don't care about your feelings crowd. Facts are facts. Anything that's got anything to do with values isn't a fact. That's just subjective. Grinnell's going to make the case that it's really more complicated than that. So that's going to be the first month or so of the class. So the next 3 weeks or so will take us about up to here. He's going to talk about the ways in which communities of scientists can help mitigate some of the potentially corrosive effects of values. So I've got a research team that's studying hypothesis X. You've got a research team that's studying hypothesis not X. We've both got built-in interests, and we can perhaps see things about each other's research programs that I can see something about your research program that you can't see. You can see something about my research program that I can't see. And if we are willing to have a serious conversation and openly exchange ideas, we can both be better off. We can both increase, in some sense, the objectivity of our research, but not because we're value-free, but because we're deploying values in the right way and in the right kind of social organization. He's going to talk about the credibility process. So how do you go from having made some observations and turning it into a journal article, and then from the journal article, how do you turn that into a sort of established and accepted scientific fact? Something like that. Yeah? Okay. So, and that'll be it for Grinnell. Then we'll kind of shift into some more traditional philosophy of science questions. So here's one that I said last time that I'm going to try to avoid, not realizing that I put it on the syllabus. The problem of what we call the demarcation problem. So how do you distinguish between science and things that just kind of look like science? What makes something scientific? This is a kind of traditional problem in the philosophy of science. I think we'll look at Karl Popper. Have we heard of this guy? So, like, if you had to come up with a rule, just off the top of your head, if you had to come up with a rule for distinguishing what makes something science and what's not science, what would you say? Yeah.
Coming up with hypotheses that are testable and falsifiable.
That's Popper's thing. Testable and falsifiable. Yeah. Is that enough?
It has to, well, there's the reproducible aspect where you have to be able to reproduce the test.
Yeah.
And the other people who reproduce it have to be getting the same results.
Right. Okay. So we talked a little bit last time about what's called the reproducibility project and the replication crisis in psychology. So I take it that psychology is in fact a science, but they're having a heck of a time reproducing some of their main results. So large-scale projects have been done. I talked last time about, I think it was 28 of the most important results from recent psychology and tried to reproduce them, and they got about 14 of them to reproduce. So big troubles doing this reproduction thing in psychology and in some parts of biology, biomedical science, some parts of chemistry. Yeah.
And to bring it back to pseudoscience, so there have been situations where people have tested whether or not psychic powers telepathy works.
Mm-hmm.
And there's
I've looked at that research. It's interesting.
Yeah, there's some people who have claimed to be able to do it.
Yeah.
But anyone who's attempted to reproduce those tests have failed to come up with the results that we've seen.
Well, that's a bit too quick. So the research on the sense of being seen is very interesting. So you sit somebody, it's a very easy experiment to do. You sit somebody down facing this way, and you have somebody behind them either looking at them or not looking at them. And you just ask the person, are you being watched or are you not being watched? And there's a group of people, there's been dozens and dozens of attempts to reproduce this. And some people did find an effect. Actually, lots of people found an effect. Unfortunately, it seemed that the groups that found an effect correlated strongly with the groups that believe that it's a thing, and groups that don't believe that it's a thing didn't find the effect, which is a bit worrying. Like, your belief in the hypothesis shouldn't have an effect on whether you find an effect or not. So there's not what you would call, I don't know of any credible scientific evidence for ESP or telepathy or anything like that. But that isn't that just. But they really did try to reproduce it. A bunch of people did reproduce it, and I think that's an important lesson on reproducibility, which is having found an effect in one study and even having reproduced the effect really isn't enough to tell you that it's true. But that does sound like good science, though, doesn't it? Like you can do legitimate testing on weird stuff like ESP and telepathy. In fact, some of the first ever blinded trials were done on was called animal magnetism. So for a while there was in Victorian England, I think, there was a kind of movement of people who thought you could do healing by like extending a living magnetic field, and it's kind of like Reiki. And so one of the earliest sort of placebo-blinded trials was put somebody behind these people thought they could sense these fields of animal magnetism. And some clever person said, okay, let's see if you can do it from behind a blind. So they just put a blind between the person and said, tell me if there's somebody there or not, tell me what their illness is. And they couldn't do it at all. So that sounds like pretty good science to me. So some of the like early advances in the scientific method came out of studying stuff like that. So just because you've got a kooky subject doesn't mean that you're not doing real science, right? Right? Actually, some of the best science, or some of the kind of driving force behind developing the scientific method, was precisely for looking at things like that. Yeah.
Well, one of the things you encounter in fringe science is that sometimes it's difficult to distinguish the real scientific concepts versus something that somebody's made up.
Is that exclusive to fringe science?
I mean, maybe. I'm not sure whether, but like, well, so if you look at physics, like physics has gotten so complicated that with the new theories that you encounter, it's really hard to tell the bad theories from the good theories.
We talked about that a little bit last time.
Okay.
So for example, string theory. Is string theory science? And you might say, well, is it testable? And what you have to say is, yeah, it's testable if you can build a particle accelerator the size of the solar system. That's how you would actually test string theory. Currently, we have no way of testing it. And it's got so many free tunable parameters. String theory is not just a theory, it's actually like a collection of possible theories. And there's so many possible theories in the collection that pretty much anything you could observe would fit one of them. So is string theory science or not? Falsifiability is an interesting one. Karl Popper famously said that the theory of evolution is not scientific because it's not falsifiable. It's not falsifiable, at least because it's sort of true by definition. So Darwinian's theory of evolution by natural selection says if there's a population with inheritance and variation, then fitter animals will tend to take over the population. Okay, Darwin, what do you mean by fitter? I mean those animals that leave more offspring. Well, that's just true by definition. But the things that I just said first, that falls out by definition. If you mean by fitter, you mean leaving more offspring, then of course those animals that are fitter will leave more offspring. So there's no experiment that could falsify it. Therefore, Popper says, it's not science. Does that sound right to you? Theory of evolution is not science because it's true by definition? Yeah.
It's true by definition, then that's not really, like, yeah.
Then who cares?
Scientific, but like.
Right.
It is, like, well, like, I mean, like science, no, it's not, it is, like, science isn't supposed to start with a conclusion. Like, or not start with a conclusion, but it's not supposed to already have the answer. It's definitive. Like, we never assume that even things like gravity, like, we know that gravity, something like gravity is real, and that we have to go on the assumption that what is being proven is real. Is not real, but is accurate until someone comes along and disproves that.
So you're saying, I mean, and this is actually a pretty common part of the definition, so when we're trying to distinguish science from pseudoscience, it's got to be something that's sort of chancy, or something that's what philosophers say contingent. It's not a guarantee. So you might say that math is not science because 2 + 2 = 4. There's no way to disprove that. It's just true by definition. If you know what the numbers 2 and 4 and plus and equal, if you know what all those things mean, then you have to agree that 2 + 2 = 4. So there's no possible experiment that could falsify that. Yeah.
I think it might not be that there's no possible experiment that can falsify it, but that we don't currently have something that can falsify it.
Even 2 + 2 = 4?
We don't currently have something that can falsify
I think it's conceptually impossible that it's falsifiable. I think if you know what those terms mean, just knowing that it doesn't, you don't even need to make observations to know that's true. Just if you know what those symbols mean, you should agree that 2 + 2 = 4.
But I'd say that's also not science.
Also not science. Okay, that's okay. So this is part of the, this is why, like, I'm not super comfortable that this is a question because, I don't know, concepts have fuzzy boundaries and who cares really what falls into the boundaries. I mean, if you're willing to say 2 + 2 = 4 is not science, but it's true and valuable, that's okay. Yeah.
I almost want to say, and this sounds very societal when I get stuff, but how you distinguish science from pseudoscience is what is kind of acceptable by the community of scientists.
Right, right. So I think that's might be as reasonable as anything that you could say, actually. So what has counted as science has changed substantially over the centuries. What gets to be accepted as science has radically altered as we go along. So it used to be, you know, Newton sitting alone could do one experiment, and that one experiment was considered a scientific result. Now we want not just one experiment, we want repeated experiments, and we don't want just one group of people to do it. We want meta-studies collecting those things. And now we're actually kind of wondering whether our meta-studies are any good. It's really hard to run a meta-study, to collect a bunch of different experimental groups' results together and say whether they fit or not. So we continue to change what counts as reliable scientific knowledge as we get better and better at this process. Yeah?
I also think that, like, it's hard to say that it's not science, it's not falsifiable, because like every like scientific discovery we have now, like at one point was falsifiable. Like in the case of evolution, like before Darwin like figured out what that was, like it would have been falsifiable at the time because he was like the person to like figure out what it even was. So even though now we know it's true based by its definition, at one point it was falsifiable because he didn't, like no one knew what it was. So like even though it's not falsifiable now, like it was in the past. So like.
So falsifiable is supposed to mean that it could be proven wrong by an experiment. Yeah, so like it might not have been, like there wouldn't have been any way to falsify it before you can't falsify a theory before you come up with a theory because you don't know what experiment to run to show that it's wrong. So, but it would have been something, I mean, okay, so let's come back, okay, well let's come back to this when we can, well, about a month from now, we'll come back to this and really discuss terms and really nail down what we're talking about. Yeah, another quick one, yeah?
On the subject of 2 + 2.
Yeah.
I don't think that 2 + 2 necessarily equals 4.
Okay. Now we're doing philosophy, all right.
I think we've all just agreed that it equals 4 because it's easier that way.
Okay.
No, because you could say 2 + 1 = 4 if 1 meant 2.
But that's denying reality.
No, that's denying what we.
Okay. Okay. You guys. I can't have you. You always got to be coming through. I can't have you like starting things between each other, or we're just going to descend into chaos and madness. And yeah. Okay. So yeah. Hi. Yeah.
I would also like to like point out that our studies on like dreams and dreaming and sleep are considered science, but most of them are just like they're like there's no proof about whether a dream would have meaning or not.
Oh, I see what you mean. Yeah. So the sort of like dream interpretation or something like that. So that was actually one of Popper's main concerns when he developed what he called his demarcation criterion was the way that Freudian psychology got treated, something like that. So the very early dream interpretation stuff and his whole sort of like psychological matrix. Popper was looking to kind of exclude that from the realm of science. Freud and Marx were his big concerns. So he says, like, look, you Marxists, anything that happens, it seems like you've got a Marxist interpretation, therefore your interpretation can't be falsified, therefore it's not science. And he thought Freud could do the same. So if you had a dream that okay, I'm not gonna, it's too weird to get into Freud here. I'm not gonna do that. But yeah, so this is one of the things that Popper was particularly concerned about, that kind of theorizing. I don't know, is astrology falsifiable? It generates predictions. Mercury's in retrograde, you're not going to be as good at language.
Well, you kind of can run tests on astrology to see whether those predictions are accurate.
So it's science.
No, it's just, when you run a test and find out that the theory's wrong, so you have a way of proving that it's not science in that situation.
I sense a lot of interest in this topic. Maybe I should have spent more time on it in the course. Yeah, yeah.
What about the fact that with astronomy, if you look at any of the results,
Mm-hmm.
look at the constellations, like apparently I'm Sagittarius, but then I look at Gemini and there's like at least 5 different qualities there that I identify with as well. I know it's based on my birth, but like if it has like the same, if you can, the whole point is that like that constellation is supposed to be unique to you, but then you can find like other constellations that would also work with you. Doesn't that kind of move your results? It just kind of is convenient for whoever you're.
Serious astrologers think that what you find in the newspaper is not nearly adequate. So that's what you described as your sun sign. You also need to know your moon sign, your rising sign, so that deeply modifies. So your sun sign is how you see yourself. Your rising sign is how other people see you. I had a girlfriend who was way into this stuff once, so I had to learn a whole bunch of astrology, just have conversations with her. But yeah, so they would say, an astrologer would say, you can't just look at the sun sign, the thing you see in the newspaper. You have to look at your whole natal chart, and the whole natal chart is much more specific. Let's not get too deep into this. Okay, I saw another hand. Yeah. Yeah.
Oh, I was just going to say that, yeah, there's different sections of your chart, so you have to do your whole birth chart with like
Right.
the time that you were born and where you were in your like
That's right.
different signs will tell you different aspects of the personality.
Right, right. There's actually a whole lot to interpreting a natal chart, and it gets way more. If you get beyond sun sign astrology into the entire natal chart, it gets much more specific. But again, let's not. We've been a long time on this one slide, and I was just going to briefly skim over this because I hate this question. Okay, yeah, quickly, yeah.
Okay, yeah, just one more thing. I don't think that the falsifiability thing, I think it's a really, really good thing, but I don't think it's completely concrete either, because whether or not a piece of information is falsifiable is totally dependent on the criteria that we have for our information, and isn't the whole reason that we're in this class because we can't always have it,
Right.
Like you were
Right,
saying.
right. Well, you can't always tell. So I think that's exactly right. The falsifiability itself is a kind of vague notion. So for example, if you find an anomalous result, does that mean you should automatically throw out your theory? A couple of years ago, there was a group of scientists very seriously worried because it looked like there were particles moving faster than light. Their experiments showed particles moving faster than light. And you might say, well, that falsifies Einstein. Chuck out all of relativity. It turns out that they hadn't quite tightened some cables hard enough, and that was the explanation. But it would have been really foolish for them to see, this data doesn't agree with the theory, therefore the theory must be wrong. That would have been really silly. Yeah, because they needed to plug in a cable a little bit harder. So it's certainly not the case that we should just, anytime data comes in that disagrees with the theory should just go. And then the question is, how much disconfirming data do you need before you're willing to throw out the theory? How strong should it be? What type is it? That kind of thing. So, sorry. How far am I through this? Should we? Okay. Assuming we don't have any more long conversations about these slides. I think there's not enough to warrant a break. We should just sort of plow through. Usually I won't go more than 50 minutes without a break. Today, is everyone okay to just kind of keep plowing through? Okay, yeah. The 2 + 2 = 4 thing, that's philosophy of math. It's a whole course we could do on philosophy of math. Is it invented or discovered? There's a massive debate about it. We did a little bit in my metaphysics class last semester, but there's a whole debate about that. Anyway, okay. So on this subject of data that comes in that doesn't agree with the theory and what do you do with it, this guy, Thomas Kuhn, he's one of the most famous people in philosophy of science, has a pretty elaborate story about that he tells in this book, The Structure of Scientific Revolutions. This really changed philosophy of science. It came out in the 70s, I think it's early 70s, 60s, 70s, something like that. Before then, so remember the 2 questions that I started with, how does science work and how should science work? Before Kuhn, philosophers of science really only looked at the how should science work. So they're these really idealized models, so they're perfectly rational sounding ways of gaining information. They didn't really pay attention to the history of science. So Kuhn does this really fun thing where he's both a philosopher and a historian of science. So I got my PhD at the Institute for the History and Philosophy of Science and Technology at University of Toronto, where we do HPS, History and Philosophy of Science, the integrated sort of study of both of those questions. How does it work? How should it work? Turns out it's really easy to come up with answers to one of them. So it's easy to answer how science should work if you ignore how it does work. And it's easy to come up with answers about how it does work if you ignore how it should work. Getting answers that match both of those questions is the tough bit. So Kuhn started off this project of trying to match philosophy of science to the history of science, which I think is the best way of doing it. And what he found was, so he's the one who talks about paradigms and paradigm shifts. So you're chugging along, you're in Newtonian mechanics and everything's going great. You're on top of the world, you're predicting things, you're building bridges, cannonballs land where you expect them to, everything's going great. And then weird stuff starts seeping in. So results that don't really fit the theory start cropping up. And you got 2 options, basically. You can say, it's a mystery. One day we'll figure out how this fits into Newtonian mechanics. Or you could say, I think we're going to have to chuck this whole thing out and start from scratch. I think we're going to have to do something quite new. And scientific communities amongst themselves sort of make this almost like a phase transition from one to another, like water boiling is a phase transition. So at some point, Kuhn says, you get what's called a scientific revolution. Most of science, 98% of science, is within some paradigm, within some set of assumptions and beliefs. And 98% of scientists spend their entire careers using those assumptions and beliefs and working out kind of the details of doing what Kuhn calls puzzle solving, sort of deploying the paradigm to solve problems within the paradigm. And then slowly but surely, typically, anomalies start building up. Things that the paradigm can't deal with, questions that it can't handle, kind of bubble up and accumulate and accumulate. And it kind of builds pressure inside the community for something new. Typically, they're like Kuhn thinks, he doesn't put it this way, but scientific communities are like, those people that never leave one relationship until they got something else lined up. You know what I mean? So he thinks scientific communities are like that. They don't break up with their current partner until they've found somebody that they think is more attractive. So when there's enough pressure within the paradigm, enough anomalies built up, and then something new, potentially new, comes up that maybe solves some of those problems, then you might undergo a paradigm shift where the community starts working with new assumptions, new methods, new ontologies, beliefs about what exists in the world, that kind of thing. And the Newton to Einstein is the most classic one. But then this raises the question about, so remember this linear model of science that Grinnell's going to critique, it raises the question about whether scientific progress is kind of really progress, because in some sense, so I don't want to go too hard on this, but Kuhn says some weird stuff like the scientists who live after Einstein lived in a different world. Yeah? The kind of problems that were important before are no longer important. New problems become important. So the world is not just, it's not just like we know more about the same world. In some sense, the world is transformed for us. Now that's probably much better interpreted as a metaphor than a literal talk. So I don't think that we should interpret that literally. Some people go hard on it and really think that, oh no, Kuhn is saying that like the world is literally transformed. I think if you read other stuff that he wrote, he doesn't mean it literally. But people really do wonder about the kind of nature and quality of scientific progress when it's punctuated by these revolutions. So we'll talk a little bit about this, about the kind of way in which scientific progress seems to be structured. I think it's really, I find it very intuitively, very difficult to deny that there is progress. Some of my colleagues from grad school, particularly the historians, thought that was hilarious. They thought it was cute and naive that I thought science makes progress. We never came to any agreement on it. Anyway, okay, so we'll talk a little bit about Kuhn. We'll then talk about, here's the funnest guy in philosophy of science, Abend. He argues for what he calls methodological anarchism. So it's tempting to think that there is a scientific method, one single scientific method. Abend is going to argue that actually in science, he says anything goes. So you can use ideas from anywhere, you can use methods from anywhere, and that the optimal way of doing science is really not to have a method at all. You just do whatever works in the moment. So that's a pretty extreme position. I think he took it on purpose to be provocative. I don't just think that because it's provocative. He says he took it to be provocative. This was supposed to be a conversation between him and another, I think it was Lakatos, another famous philosopher of science, said, hey, Paul, write me a book that's super outrageous, and then I'll write a book in response. And then Lakatos died, unfortunately, before he could write the response. So all we've got is Abend being extremely provocative. But he's going to make the case for what he calls methodological anarchism, the idea that the only rule that makes sense in science is that anything goes. And he makes the case through the history of science. So here's just one of his examples. Galileo, he's a good scientist, right? Pretty good scientist. If you look at the details of the arguments he was making, like, they're not that great, frankly. So Galileo says things like, hey, the Earth is spinning round and round once every 24 hours. And they didn't at that time have the notion of inertial physics. So people very sensibly said to Galileo, all right, smart guy, how come we don't go flying off then? The Earth is spinning round and round, how come we don't go flying off? And he really didn't have much of an answer. So he eventually develops inertial physics as an answer. But that sounds kind of ad hoc, right? He presents his model, they prevent a devastating critique, and then he comes up with a new theory to deal with the critique. Well, that sounds like you're just covering your butt, doesn't it? But he's Galileo. Like he's right. I mean, he turns out to be right about practically everything, or at least he does in some relative sense. I mean, he's the precursor to Newton. So ignoring the best available arguments turns out to be, for Galileo, a really good move. A really good move. And Abend takes this and a whole bunch of other examples to say like, hey, maybe you shouldn't follow the rules all the time. Maybe sometimes ignoring the best available arguments is the best move to make. Worked for Galileo. So we'll do that because I think it's super fun. And he's very provocative. You're not going to get grants if you act like this, but it's interesting nonetheless. Okay, and then we're going to do a little bit about, this is kind of old-fashioned. This is from the notion of social construction. So there was a fad in the 1990s that back when most of you were you alive in the 1990s? Yes, most of you were alive in the 90s. Okay, so in the 1990s we had what were called the science wars. It wasn't as dramatic as the coming World War III, but the science wars were this sort of like sustained critique from the humanities of the sciences. And what they were saying is science is a social construct. They were saying, look, what you're presenting to us as objective facts are actually social products. And this was meant to disarm some of what they perceived to be excessive social power and excessive epistemic power of the sciences. Now that it looks like we're all going to die from climate change, people are less hyped about this project. Now we want them to believe scientists. We're all going to die from malaria because of the anti-vaxxers and climate change. So now very few people are beating their chests about trying to disarm the sciences as a sort of social force. But for a while there was this pretty sustained critique because I guess we didn't care about those things yet. So we'll talk a little bit about social construction, what it means for something to be socially constructed. I think there's a very good case to say that any product of science is a social construct, because science is a social process. But does that mean that it's all made up? So when you say something is a social construct, it sounds like what you're saying is it's all made up. But money's a social construct. I take it that we all care about that, right? So what exactly it means to say something as a social construct, what that sort of entails, is something I think that's worth thinking about a little bit. We'll do a little bit of this. Grinnell will do a little bit of this because, of course, he does think that science is a social process. He quite correctly identifies that science is a social process. It's not just like one person doing science. If you read the sort of like who gets credit for any major scientific paper now, there's like 50 people on there. So science is a social process, but what does that mean? What does that entail? So we'll do a little bit of that. Again, it's a little old-fashioned, but whatever. Then we'll do a little bit of so I'm from mostly analytic philosophy of science, where we do boring technical stuff, so I'll force you to do some boring technical stuff. Scientific explanation. So what does it mean to say that we've got a scientific explanation of something? And can everything be explained scientifically? This is the general schema for what's called the deductive nomological model of scientific explanation. So you've got some fact plus a general law that entails the thing you're trying to explain. This turns out to not work at all. Well, it only sort of works. It certainly doesn't work for all kinds of explanations. Philosophers to this day are having a lot of trouble coming up with a general account of scientific explanation. So we'll do a little bit of this. I think it's interesting anyway. And we'll turn to. So with this stuff about scientific explanation in mind, so just to come back to this, so in the 50s, this was the model in the 50s of how scientific explanation works. You've got not just general law, but a universal law, some statement that's always true. So copper is conductive, or electrons are negatively charged, or something like that, yeah? Some very, very general law. And if you're explaining something scientifically, they thought, this is what you need. So you need to subsume it, they say, under a general law. And then we might want to think about something like biology, where it's like, there really aren't that many general laws of biology. Practically everything, and some people say everything in biology, is full of exceptions. So everything from biology on up seems to be riddled with exceptions. So there's no universal laws in biology as far as anybody can tell. At least that's a consensus amongst biologists. So the deeper somebody is into the details of studying living things, the less convinced they are that anything is always true about living things. Maybe there's some very, very general, like living things are made of matter. Like maybe you can say something like that. But if you want to get into anything like the details of how living things work, all of the rules of biology seem to be full of exceptions. So what we'll spend a week thinking about, does that, if explaining something means fitting it into a universal or a general law, can you explain anything in biology? Seems like you should be able to, right? What does that mean for the way we think about sciences? So one of the issues with 20th century philosophy of science was that it really focused on physics as the science. Physics was the science. And it's not clear to me that all sciences behave like physics. Biology seems to have a different kind of character in a number of ways. I'd like to kind of explore a little bit the differences in character. So, following on that, we'll do a week on functions and purposes. So, it's extremely common to, any of you who are in my philosophy of mind class heard me rant at length about how the scientific revolution banished functions and purposes from the world. So Aristotle saw the world as full of meaning and goals and all that kind of stuff. And then the scientific revolution comes along and says, nah. It's just mechanisms. It's just blind mechanisms churning away. We're going to explain everything in terms of just mechanical forces. But at no point in that process did biologists stop talking about so for example, the function of a heart is, the heart is for pumping blood. That's what it's for. That's its goal, it's its purpose. So, yeah.
Well, isn't biology fundamentally different because the nature of a living organism is that it has some kind of goal or objective because it's self-sustaining and attempts to perpetuate itself?
That's, I think, very reasonable, but not a super popular view in this stuff. So the alternative to that is to say something like this. You might say, okay, you want to say the heart is for pumping blood. That's really just shorthand for something like evolution selected for hearts that happen to pump blood because, we end up seeing hearts that pump blood because if your heart is bad at pumping blood, you don't get to live and therefore you don't get to reproduce and therefore you don't get to pass on your genes. So that's a much longer and more cumbersome sentence, and we might say, we're just going to shorthand it to hearts are for pumping blood. So, this is the debate that we get about functions, right? Is that just shorthand, right? Is talking about functions and purposes in living things just a convenient way of compressing that long and rambly thing about evolution down into something short and handy? Or is there actually a fact of the matter that, no, actually hearts are for pumping blood? Living beings really do have goals and purposes and aims and things like that. So that's the debate. That's the debate I'd like to touch on for like a little bit. Yeah? Yeah. And then finally, just for fun, we'll do 1 week on science and the meaning of life. So when the scientific revolution comes along, and the sort of meaning and purpose gets stripped out of the natural world, you might wonder, can life still be meaningful? So if we're going to live in the scientific worldview, so for a whole lot of people, like I was raised without religion, I don't have a religious framework to say, I know what I'm here for. I kind of envy people who have a religious framework because you're like, I know what my purpose in life is. It was given to be by my creator. I believe that my creator was a very long process of evolution. And so I often wonder if there is some sense of meaning that I can, maybe objective meaning that I can recover within the scientific worldview. So I'd like to spend at least 1 week talking a little bit about that. Is there or isn't there a real substantial sense of meaning? Of course, we can have a feeling of meaning, but is there something in the world that corresponds to that feeling, or is that just a sort of a comforting illusion that we give ourselves so that we can get through our days? I think that's a very serious conversation that we should be having about how to live under the scientific worldview. So we'll end off with that, just for chuckles. Yeah? Okay. So that's more or less the course. That's the plan. Start reading Grinnell. So for next week, we're going to read chapter 1. Chapter 1's the only reading for next week. It's pretty short. It's like 20 pages or something like that. Read it, think about it. We'll dive into it. That's it for today. Okay. Thanks, everyone.